Can anyone confirm if audio and everything is fine? Sorry for a bit delay here. And like I plan to discuss A, B, C, D, and F and G definitely. Like if people in the chat can say solution for E, I might discuss it. But yeah, in the contest, I was not able to get it. So that's where we are. So before we get started, can anyone confirm if audio and everything looks fine? And yeah, like I will discuss 360. So let's get started. Once, yeah. Mhm. Okay, it says there is a stack of n cards. The ith card from the top has AI written on it. You take k cards from the bottom of the stack and place them on the top of the stack, maintaining their order. Print the integers written on the top to bottom after this operation. So here, like probably if you look at 1, 2, 3, 4, the idea is like you look at the last three numbers and put them at starting, and the number becomes 3, 4, 5, 1, 2. So like initially 1, 2, 3, 4, 1 is at the top and 5 is at the bottom. So you look bottommost three integers and put them at the top. Similarly, like it's not necessary the numbers written are distinct, by the way. For example, 1, 2, 1, 2, 1, 2. If you look at top two numbers and put them at first, the order becomes 1, 2, 1, 2, 1, 2, 1, 2. And I think Grundy number I explained in last code forces round. So pretty much the idea for this problem is also same. So the idea is like you can either use rotate method present in C++, or you just know that, like for example, if you remove the last k numbers, you should start printing from here and then you can print these numbers. That too works. So probably I will share my solution now. One second. So like first let's find the index of first element, which would be n minus k because you want to remove k numbers from last. You print the numbers from first element to last, and then you print all the numbers from the first index to the first element here. And this would be our solution here. So this was the first problem. Let's probably move on to second problem now. Second problem says like you always take two maximum element, decrease them by 1. And basically you are given a sequence of n positive integers a1 to an. Takasi repeats the operation until a contains one or fewer elements. Basically sort in descending order, then decrease both a1 and a2 by 1 and count the number of times he needs to perform this operation. Here n is up to 100, all ai are up to 100. So like you see like the maximum number of operation you can have is like when everything becomes 0, and 100 like sum of all elements by 2 is the maximum number of operations you can have. So like the first idea would be to just keep brute forcing it until only one element, positive element, remains. Like you sort elements in decreasing order, number of operations is 0. As long as a1 is greater than 1, you increase a1 plus plus, a0 minus minus, a1 minus minus, then sort in decreasing order again. And at last print the number of operations you did. So like this would be the plain brute force solution. And you can see like the number of operations required, the upper bound on the number of operation would be 100 into 100 by 2. Like sum of all the elements by 2, you cannot have more than that, because in each operation you are decreasing elements by 1. So this is one solution for it, by the way. And there is one way to do it even faster. You can see like in each element, yeah, brute force was accepted. Let's find sum of all the elements. And like let's also find sum of all the elements, other than maximum. And my claim is like the answer would always be minimum of these two. Minimum of sum by 2, like you cannot have more than that, and sum of all the elements other than 0. This is another solution, like you can probably now do it, see, you can do it in order and time. And like how do we prove this as an upper bound? Like this is obviously an upper bound, because in each operation you decrease total sum by 2. So like the number of times you can decrease total sum is like, if let's say the sum is 7, then you can only decrease up to 6 in 3 operations. Or if sum is 8, then you can only decrease 4 times and 2 times each time. That's how this comes in. And this is probably like the only corner case when you cannot get sum by 2 is when at every time like the maximum element is more than sum of all the other elements. Let's say like for example your sequence looks like this. Let's pick some element 1, 2, 3, 4. In this case total sum is 10 and you would be able to get 5 operations here. But like in this case you see 1, 2, 3, 6, 20. In this case maximum number of operations you would be able to do would be only 6, because after that all the element other than maximum will decrease by 0. And essentially that's the idea over here. So like we have 2 upper bounds and answer is minimum of both of them. So any questions on first 2 problem before we move on to problem C? Okay, I will move on to problem C, triple attack. It says you are playing again. There are n enemies lined up in a row. The ith enemy from front has health touch. You will repeat the following action until the health of all the enemies become 0 or less. Using a variable t initialized to 0. Increase t by 1, then attack the frontmost enemy with health 1 or more. If t is multiple of 3, enemy health decreases by 3, otherwise it decreases by 1. Find the value of t when the health of all enemies becomes 0 or less. So here the idea is, let's say before you start attacking an enemy, like the main idea was like if you do 3 attacks on an enemy, the health decreases by 0. Like for example, let's say start with t equal to 10. After first attack health becomes 1. After second attack health becomes 12. After third attack health becomes 1. In this case minus 1 happens. In this case minus 3 happens. In this case minus 1 happens. Similarly, if t is 11, after first attack the health becomes 12, 13, 14. In this case minus 3 happens. In this case minus 1 happens. In this case, minus 1 happens. Similarly, for example, if t is 12 plus 3 at x, health is 13, 14, 15. Minus 1, minus 1, minus 3. You can verify no matter how we are doing. For every 3 consecutive attacks, for every 3 attacks, monster gets minus 5. So now what we can do is, like, let's say if a monster's health is, let's say, 14. We can say, like, to decrease minus 10 first, we would need 6 operations. Or let's say monster's health is 21 first. Then we can say that minus 20 will happen because of first 12 operations. Because for every minus 5, you need 3 operations. So minus 10, you would need 6 operations. Minus 15, you would need 9 operations. And minus 20, you would need minus 9, 12 operations, and so on. So what we can do is, like, we can start processing enemies. And first we can do attacks of 3 each time, decreasing health by minus 5. When health becomes less than 5, we brute force the remaining part. And like this would be the main idea I have. First, I see how many batches of 5 I can attack. That would be x divided by 5. Number of attacks required would be 3 into f, and now x becomes this. Now, as long as x is greater than 0, do attack on this. And essentially this was the solution for the problem. Because the idea is, now after this step, the x is less than 5. And because x is less than 5, this for loop will not run more than 5 times in the worst case. So overall the time complexity would be order n here. And like this was the solution for the problem. Any questions on first problem before we move on to the next problem? Yeah, you can definitely try to do binary search here, but that's not required. What if we want to generalize to k? Like, it would probably require order k elements here. Like, this for loop will run probably order k here. And that would be the idea. And if you want to do it faster, you can probably do a binary search on number of operations required. Let's say if you do 10 operations from here, you know the starting value of t. So you can find out how much damage you would do in the next 10 operations. Then, like, probably you can start with something low, something high. Look at mid. You look from t plus 1 to t plus mid, how much damage you can do. Is it less than x? If that is less than x, then you have to probably increase your lower bound. If mid was the maximum required, then you can decrease your upper bound and keep going over there. Yeah, probably I can take a look at submission on the Discord server. For the stream, I will probably continue discussing the further problems. Problem D says minimum Steiner tree. You are given a tree with n vertices numbered from 1 to n. The ith edge connects vertices ai, bi. Consider a tree that can be obtained by deleting some possibly 0 edges. and vertices from this graph. Find the minimum number of vertices in such a tree that includes all the k vertices which have been given in the input. Let's look at some samples to see how it's happening. This is the first tree given to us. It says we want to delete some edges, but 1, 3 and 5 should still be connected. So like for example, in this case, we want 1, 3 and 5 to remain. So you can see like on path between 1 and 5, 2 also comes here. So we will have to keep 2 as well. That's what we want. You see, if we notice 4, nothing happens here. Similarly, if we delete 6 and 7, like 2, 1, 3 and 5 would still remain connected. So the answer in this case is 4, like we will have to keep 4 vertices. In the second sample, it says like this is how the tree looks like after you delete the other vertices. In the second sample, there are 4 vertices, you have to keep all 4 of them. In the last sample, you have only 1 vertex, so you can just keep it. Or probably if you want to generalize it, my solution would be to pick any node as a root which we want. We should take it. Like root is definitely the one of the node which we want to keep. And let's see our tree looks like this. Now if we have to keep this vertex also, because we also want a root, then we will have to keep every vertex on this path. Similarly, let's say if we want to keep this vertex, then we will have to also keep every vertex on this path up to root. So the idea is if you root the tree at one of the vertex you definitely want to keep, then like you can do a DFS, and you can have for every node you will have to also keep all its parent as well which you want to keep. And that basically means like for any node. So for example, like let's say we have also a node like this. If this subtree does not contain any node which we want, then we can definitely delete this node as well. And this is the main idea for this problem. We take all the vertices graph as input first. Then we create a set of all the vertices which we finally want to keep. If we only want to keep one vertex, just print one and call it a day. Although this is not required strictly. This special case was not required. Otherwise, do a DFS starting from any one node which we want over there. Any node works. Then we have for each variable we are doing a DFS, and we have a variable take which says should we keep this variable as well. If the current node is in the set, we should definitely keep it in the remaining. Otherwise, do a DFS. If there is some node in the subtree which we want to keep, then we have to also keep the current node as well. Because like this DFS definitely returns true if there is a node in the subtree which we want to keep at last, and false if we do not want. If there is a node in the subtree which needs to be kept, then current node should also be kept. So we mark it as true. And at last we return whatever the result was. And if this node should be kept, then we also do answer plus plus. And this was the idea for the problem D. Any questions on problem D before we move on to problem F first? Any questions on first floor problem before I move to F and G? What happens if you pick a node where left and right are the nodes we want, but picking a node that is on the path edge of a path? Like, I'm not sure if I got you here. Okay, can you give me an example? I can probably try to run it on the example and see what should be the case. So for example, if you want 1, 2, 3, 4, and what are the edges we have? Okay, so let's say we have routed the tree at 1. Five, 4. And then let's say something more happens here. Let's say we have a subtree like this. So you see, like, when you return from a DFS of any node from here, you will return a false. So you will end up deleting everything from here. Because you want to take this DFS will in fact return true. So we will also preserve 5, but all the nodes here will also return false. So these will also be deleted. These will also be deleted. These will also be deleted. But because this 4 needs to be present, this 4 DFS will return 5. True for 5. 5 DFS will also end up returning true. 3 will also end up returning true. 2 will also end up returning true. So you will end up keeping 1 to all these 5 nodes. And the answer would be 5. Now, like, this is the main idea here. Like, there are some edge cases, like, and not edge cases, I would say, like, you might have to be. Does it matter if we start at 3 or 4? No, it does not matter if you start 3 or 4. Let's say if you start at 3, you will have 5 like this, 4 like this, true like this, 1 like this, and there would be some other subtrees of 3 here, another subtrees of 2, another subtrees of 1, another subtrees of 5, another subtrees of 5. This will be kept because this needs to be there. This will return true for 5. 5 will also be kept. This will also return true for 3. Similarly, 1 will also return true here. 2 will also return true here. So, and everything else will keep up returning false, and the answer remains 5. Yeah, like virtual tree can also be one of the solution, but that's strictly not required for this problem. So I will probably move to F now. It says you are given a sequence of n positive integers a1 to an, where each element is at least 2. Anna and Bruno play a game using 3 integers. They take turn with Anna going first. Perform the following operation. Choose an integer I freely. Then choose a positive integer x of ai that is not ai itself and replace ai with x. The player who cannot perform the operation loses and the player wins. Determine who wins, assuming both players play optimal for the victory. So, like, it says it's a kind of a nim game, and I would say, like, the solution is pretty much same as one of the educational problem recently. Like, solution is pretty much same as this problem. Like, at least the brute force part is same. This problem required a few more observation after doing a brute force on the nim game, but for this problem we don't really need it. And like, in the video tutorial I created for this problem, like the post contest discussion, I have in fact explained like how to do a brute force on the nim games to begin with. If you want, I can probably trim out that clip and put it as a video there, or you can probably directly refer to that problem. So like in the interest of time, I will probably skip this one. You can start watching it from here. Like I did give a brief intro of like how to solve name games, what type of like I did not give formal proofs in this video, but like I think I gave enough context to what should be required to brute force a particular problem for this. So like here I am trying to explain like how to find max 20 values, etc. Like what kind of bag, etc. looks like. So you can probably watch from here until here and you will get a crisp of what needs to be done to do a brute force here. And this problem essentially required brute forcing only, like nothing more was required. Probably I can share a brief code like so essentially like that's what I am doing as well. Like I have a function to find the max of a set as well. And like for each element, I'm looking at what all the factors of the max I can get. And like this loop ends up finding the Grundy value for each of them. And at last, you just take XOR of any element. XOR is positive, print the first player wins, otherwise the second player wins. Like I heavily recommend watching out this video. And if you want, like I can probably trim down the exact part and I can just post a video on how to brute force name games. And that can be the one over there. Like it's exactly same as that. Like only the method to do it is required and you probably need to know C algorithm to solve it. So like probably I will just end up skipping it and I will move on to problem G then. It says add and multiply queries. You are given sequence of positive integers a, b of length n. Process q queries given in the following forms in the order they are given. Each query is of one of the following. Okay, by the way, one more thing which I forgot to mention was by the way, there is one more book which I mentioned over here. Like it describes a lot of name games here, by the way. And like you might want to read it to see like how to solve the problems here. Winning your I don't remember the name. Winning ways for your mathematical plays V1. Like you don't need to read a complete book, but you can probably read some starting chapters to see like how to solve game theory problems in the book. Okay, moving on to the next problem. Let's say add and multiply queries. You are given sequence of positive integers a and b of length n. Process q queries given in the following forms in the order they are given. Each query is one of the following three types. Given the form 1 I and x, replace ai with x. Given the form 2 I and x, replace bi with x. Given the form 3L and R, solve the following problem and print the answer. Set initially v equal to 0 and for all I equal to L to R. Replace v with either v plus ai or v into bi and find the maximum possible value of v at the end. Also, the important part here is it's guaranteed that the answer of the type 3 query would be at max 10 to the power 18. And also all the numbers are positive. So like let's probably modify this problem a bit first and try to solve a different problem first. Let's say we will do it like this. We will start from I equal to L to R. If AI equal to V equal to 0. Now probably let's start with this level. V equal to AL and from L plus 1 to up to R. If Vi equal to 1, we will do v plus equal to ai, else we will do v multiply equal to bi. Let's say this is the brute force code we want to write. And you know, like, no, like I did not discuss the because I don't know how to solve it. So like you see, like the answer we get with this algorithm can be less than the optimal answer you want. But can you estimate the time complexity for this code? Or let's say here I replace it with like this. Like my final code will look like this: v equal to max of v plus ai comma v into bi. And like essentially this is the code I have written with some optimizations on it. And like overall time complexity is still order n. But the question is how many times we need this operation. Yes, the idea is correct. Like the maximum number of times you can do would be log 2 with base 18, base 10 to the power 18. Because like whenever you do this, notice that v at least doubles. Because like bi equal to 1 is handled in a different way. V into bi would multiply it by at least 2. And in case v into bi is less than v plus ai, then also like the value of b has at least doubled. So this condition, because we have been given that the answer is always less than equal to 10 to the power 18, this condition will only happen log 2 into 10 to the power 18 times, which is approximately equal to 60. So now what we can do is probably for this part, like we can use like Fenwick tree or something to find, like, let's say we are at some index I, we also have some value I. We first try to find like up to how many values have bi equal to 1. So like what I can do is like I can first try to find like up to how much values I have bi equal to 1. I can directly use a Fenwick tree to get this range sum, and I can do v plus equal to this range sum over here. And whenever I have bi greater than equal to 2, I essentially write a brute force code like this. And to find the next element greater than 1, I can keep a set of values where bi is greater than 1, and then I can probably use the lower bound function there. And pretty much the main idea was like you can probably brute force it if you do like the plus query for bi equal to 1 in one go. Fenwick tree to find range sum values, and this has I have a set which contains all the indexes where value is greater than equal to 2. So like here I have added all the values greater than equal to 2. Type 1 queries, Fenwick tree remove existing value from index, update value and add that value to it. Type 2 values, if current value is greater than 2, remove that index, update that index, and if new value is greater than equal to 2, add that index again. Now like type 3 queries, when you want to find elements from L to R, you start with IDX R, like the element you want to process, as long as you are less than index R. Yes, like I am yet to update the description. It's the last problem as well. So like if current value is greater than equal to 2, I simply do answer equal to max of sum or multiply whatever you want, and you do idx plus plus. Otherwise, if current value is less than n, you find what is the maximum next index where like you will find a 2, and you take minimum with r as well. Then whatever the range sum you have over there, like you directly take this range sum and you update the next index there, and essentially this will end up ensuring that you will not get a TL there. No, like, and this was the code for that problem. What I was saying was like if you write a brute force code, the only critical piece of code was like this condition will only happen log n times. This else can happen any number of times. This if bi equal to 1. This will only happen up to 60 times. So the idea was if we can somehow combine these queries and do it faster, group batch this, overall we would be able to just have around 120 times or so. And like that was the idea over there. And the reasoning for this was like whenever you are doing an operation like this, your value of v doubles at least. Because either you are multiplying with bi and bi is greater than equal to 2, or you are even taking the value which is more than v into bi. With that can be this case. Yes, f is Grundy theorem and mostly trying to brute force on it over there. And that's why like you will not process more than like the range L to R will not contain more than log 2 into 18 bi is greater than equal to 2, which is approximately 16. And this comes from the fact that this is given to us. And I think it might be possible to solve this problem without this constraint, where it said that the answer will be greater than equal to, like, just printed some mod. It might be possible, but I haven't really tried it. And I think these were pretty much my solutions for A, B, C, D, F, and G. Like F, I would redirect you to look at the video. Like I can probably crop that video, older video I have, and publish it at a new video then. So any other questions, people from the chat or anything else before we call it a day today? And like using Fenwick tree, what I have done is like I essentially optimized this proof. Was like I found like what is the from current element up to how further I will need have bi equal to 1, and directly take that range sum over there. And like I don't know how to solve it, so probably I will skip it. But probably I can take a look at if anyone has shared solution for you on Quattro. Yeah, lower bound b2 or greater dot begin, like yeah, this is like I am assuming like Balakrishnan b2 or greater is a set you have, not the vector, right? Like are you doing lower bound on the set or a vector? Just one question. Yeah, b value at 1 at alternative position also doesn't matter, like because like whenever you multiply by Like from constraint, if alternative value is 1, and because from constraint you know, like from this constraint you know that there cannot be more than 60 values which have bi greater than 1. So if even if alternative values are 1, then you won't have like range from L to R will be less than 120. Yeah, like the problem is like lower bound dot begin dot end on a set is order n essentially, while b dot lower bound is log n there. And like the main reason is like it's not possible to get random index on a set. So like this method end up running a for loop from it dot begin to up to it dot end. While this looks at the internal structure of red black tree or whatever tree we have and try to get the value in log n. And like I'm not sure, like random access is not possible on a set. Like you cannot just find the fifth index. So you cannot do a binary search which like the lower bound method does. Not sure what. Yeah, like I think I have updated the description. Generally, I end up using the previous video, and after I'm done with the stream, I update the description and thumbnail, etc. So not sure like the chat I have on console. Like so probably something to look out for. Like I think I have also made that lower bound mistake once. So any other questions we have? Yeah, like this is something we have to look out for. Like, sat dot lower bound is log n and lower bound sat dot begins sat dot end and x will take order and time. So I think probably I will end my stream if there are no further questions. And thanks everyone for joining today and sorry for being a bit late in starting. Yeah, like probably like I think you won't make the same mistake again. Like I have also made it once. Like okay, Saurabh Bhaja says you can solve it using sweep line algorithm. For each train, its delay depends only on the maximum arrival time of train incident on the city from which it starts. Like I was probably confused at like what happened if like because the different starting time can have different set of indexes there. So like thanks everyone for joining today, and I think I will crop my education round video and put it as a video there. Not fully dedicated video on it, but at least that goes through some of the things on how to brute force the number theory problem. Like no, I won't say it's a formal lecture, but some things to work around over there. So thanks everyone for joining today.